Professor Josh Bongard, thank you so much for coming today. How are you?
I'm well. Thanks for having me on, Roy.
Yes, it's my pleasure, and my guess that it will be also my audience pleasure because what you have to say and your research is, I have no other words than mind-blowing. But let's start. Have you ever been in Israel?
I was there as a high schooler for the Maccabi Games many years ago.
Oh, wow. Okay. And you should probably visit again, not soon, because right now.
I understand. I would love to
But
come back someday. Absolutely.
okay, so we did our Israeli Jew thing, and let us move on. You have many works that you're doing in your website and on Wikipedia. One can say that you're all a roboticist and dealing with artificial intelligence. Okay, and I
That's
want to start with the combination of the two. The other day, I ran a panel about artificial intelligence and robotics. And in
okay.
the panel was, Israeli top leading expert in robotic intelligence. For example, Shai Shalev Schwartz is a, oh, just a second, because okay. No, just a second, let me, uh, I want everything to be great, and it's not great according to my microphone. So with your
Okay.
permission, it will be, it will take
Take your
30
time.
seconds.
Take your
30
time.
seconds. Okay, I'm sorry. Something happened. Okay.
No
Let me
problem.
just one, two. Okay. Uh, can you?
I did hear you, and now I think I lost you.
Okay, just a
Oh no,
second.
there, I hear you. I hear you. Perfect.
Okay. Can you hear me over here? Yes.
I'm not sure where I'm hearing you from, but you sound crystal
Okay.
clear.
Okay. One, two
That's
from
coming
here.
from the
Okay.
microphone, definitely.
Okay.
Yep.
So I'm sorry. I'm sorry. There was like a little bit of a problem. And just a second. Okay. Okay. So, okay. We're going to replace everything. I'm sorry for the inconvenience. Okay. So
That's okay.
I will start with the other day. Okay.
Sure.
One, two, three. Okay. One, two, three. Okay. Okay. The other day, I ran a panel about artificial intelligence and robotics, and in the panel were some of Israeli leading experts on artificial intelligence and robotics, Shai Shalev Schwartz, the CTO of Mobileye, etc. And the idea was, or the question, the big question at the panel was, do we still need the conventional classical algorithms of robotics? And
Mm.
why can't we throw everything on the AI? Why do we need, like inverse kinematics? Why do we need the physical modeling of the system? Let deep learning, reinforcement learning do all the work. And my first question to you is, where do you stand in this? AI can do everything to, we still need the conventional robotic algorithm approach.
Yeah, it's a great question. I think my opinion is we still need both. It's not either or, it can be both. And this is one of the beautiful things about AI. We can incorporate into AI the generation of forward kinematics. It can generate it for whatever the robot is. And the reason why we need to retain, in my opinion, a lot of that machinery like forward kinematics is it's simple. Humans understand it, and when it makes a prediction, like forward kinematics say, this is what the robot is about to do in the next few milliseconds or the next minute. That can be very important if that robot is standing right next to a human being. You want a guarantee about what the robot is going to do. AI is wonderful and I use it. We all use it. It's very powerful, but every once in a while it makes mistakes and we can't predict when it's going to make a mistake. And that can be potentially very dangerous when we connect that kind of AI to robotics. We need simple, formal, human understandable algorithms in some cases, and in other cases, we can rely on AI, which is very powerful and can do things in non-intuitive spaces where humans can't do things very well. In my opinion, we need both.
Okay, so if I may, let me just recap your answer or
Sure.
phrase it differently.
Sure.
When you say that AI is unpredictable sometimes, what you basically mean is that the level of explainable AI is insufficient right now, or do you mean another much stronger claim that I don't trust AI systems, and since I really don't understand them?
I would say the latter. I don't trust them. I don't trust that we have a good idea how to make them more explainable or how to make them more trustworthy at the moment. That is still an open question. And until that question is solved, I don't want to be near a robot or an autonomous vehicle that is being controlled by untrustworthy AI.
And I had a conversation with Professor Elad Chazan, the one of the founders of the Adam gradient algorithms, and he told
Okay.
me when he wanted, his first major big paper was about, to incorporate deep learning in control theory, and one of the reviewers says, these Kalman equations put a man on the moon. So please give a big respect to those simple Kalman equations. Okay, don't just let substitute them for a black magic thing.
Agreed. Agreed. I think, yeah, replacing all of that with AI is not the answer. It's overly simplistic. Whatever the answer is, it's going to be to find a larger framework in which we can combine the best of both worlds.
Okay, so this is a great answer. Let's move to your book, How the Body Shapes the Way We Think. And the book was first published in 2006 and 2007. And my question is, since the Transformers, the Attention is All You Need paper was published in 2017, and the
Yeah.
world has changed dramatically ever since. My first rude Israeli question is this book still relevant?
Yeah, good. It's not a rude question. It's a very good question. Yeah. In terms of AI, 2007 might as well be 2007 BC. It was pre AI revolution. Absolutely. I would say 90% of the examples of the robotics and AI systems that we mention in that book, absolutely, completely irrelevant. I'm biased as the author of this book, but I feel that the deeper philosophical points we were trying to make about why a body is important, that is still true. And even more, it's more important today when we now have powerful AI, non-embodied AI, which is right 99% of the time, but 1% of the time it's wrong, and we can't predict when it's going to be wrong. It's even more important, in my opinion, to think about how the body shapes the way we think.
This is why the philosophy departments are so important, because they are always relevant. What you wrote, I don't know, like 20, 18 years ago about engineering might be relevant, but the philosophical ideas are still crucial. And okay, the main idea, I think, of your book, that our notion of just brain, I don't know if you're familiar with a anime Ninja Turtles, where they're like the just brain entities that can talk and communicate. The idea that women, that we as human beings are just brain and the entire body is just like a robot or like a vehicle for us is completely false. This
Completely
is
false.
basically the idea. And one can see those kinds of ideas in the writings of Melanie Mitchell, in the writing of Jan LeCun, in the writing of Gary Marcus. So it's not just what you said back then in 2006. Right now, Jan LeCun say, okay, we have LLM, but the amount of data that a 4 years old boy can get through his vision sensors is much bigger than all the LLM. So with your permission, I would like to start with the concept of, okay, let me phrase from your book, the
Sure.
kinds of thoughts that we can produce or carry out ultimately have their foundation in our embodiment. So I think that the main concept in our first part of the conversation will be embodiment. So if you can please elaborate on this very important concept.
Absolutely. So the idea of embodiment is you mentioned philosophy. It's an idea that you can trace back 2,000 years to the Greeks. You can go further back than that. But there is this intuitive understanding that brain and body, however you define them, 500 years ago, they would have said, body and soul. There's something there about these two components that are necessary. You can't have just one of them. And embodiment often goes even further in showing that body and brain themselves, whatever these two systems are, they are not actually two systems. They are one system intertwined. It's hard for humans to think about this one intertwined system, so we tend to think about the body, everything except the central and peripheral nervous system, and then the brain, the CNS and the PNS, that these are separate things. We can get into whether they're two systems or one system, but there is this growing feeling. You mentioned Jan LeCun and Melanie Mitchell and many others who are thinking about how do we create truly intelligent and safe machines. They need to literally be here in the real world with us. So embodiment means a lot of different things to a lot of different people, but here's my best attempt at a summary of what embodiment is. It is a thing that can push against the world, and sometimes that pushing is literal, and sometimes it's metaphorical. It's a thing that can push against the world and observe how the world pushes back. That feedback loop between action and reaction becomes the raw material on which true intelligence is built. Non-embodied AI systems like ChatGPT, Stable Diffusion, you name it, they cannot literally push against the world. They cannot generate any actions in the real world and observe how the world pushes back. They are non-embodied in the sense that they're passive. They have to wait for something, a prompt from a human being, and then they provide some data back as a response. That is not embodiment. Embodiment is push against the world and observe how the world pushes back. That's embodiment in a nutshell.
Your idea of pushing is extremely powerful because, the other day I had a podcast interview and I mentioned the idea of John Locke experiment, where let's say that you give a blind man a sphere or a metal sphere and a metal box. And he can just by feeling the sphere and the box can distinguish between the two. And now, says Locke, let's say that you give the man his vision, his sight back. Without touching the sphere and the box, John Locke asked, could the man distinguish between the sphere and the box? Could the man connect the idea of edges in the boxes with the vision of edges? And the answer is no. And this is mind-blowing because the idea we need to push back, the idea of feedback that we get from the outer physical world is very, very, very important. I need to come up with another adjective. But
well, I would say it's the opposite to looking at something. When you look, stuff is coming in. When you act, the action comes first. And the definition of edge, of an edged object, is I do this and I feel this. That's embodiment.
So without this crucial feedback, one cannot understand the works. The idea of Immanuel Kant, the distinction between the nomen and phenomenon, can be depicted very easily in this scenario. So my question is, we know that in LLM we have like RLHF, reinforcement learning human feedback. Can you please elaborate why the human feedback that we have in LLMs is profoundly different than the feedback that you and me are talking about when we are saying that we push into reality?
Yeah, a great point. So reinforcement learning with human feedback, RLHF, for those that are not familiar in your audience, basically that's a machine recruiting as many people as possible to act, to be the embodied proxy for this thing that's non-embodied. The non-embodied thing basically asks these humans to go out and provide examples of things that work and don't work in the real world. And this would be the equivalent of reward and punishment. I would say that's a step in the right direction. So, the easiest thing is to think about black and white thinking. This thing is non-embodied and this thing is embodied, and you need to have embodied things. And that's okay. But of course, in reality, there is a large number of machines and technologies out there, and some are more embodied than others. So I would say RLHF is a step in the right direction, but it's still lacking a lot of important things that embodied systems tend to have. And we can talk about what some of those differences are, if you like.
But before we do, let me just quote another paragraph from your book.
Sure.
Somewhat provocatively, we said that we will challenge the classical notion of the brain controlling the body, and we will try to show that the computational theories of intelligence are doomed to failure. We will also, along the way, attempt to dismantle the myth that machines cannot be creative. Okay, so before we dive into the non-creative machines, we still, on reason tests, okay? And we have many reason tests, GPT-4, GPT-4o, Claude 3.5 are doing pretty well. We had this Microsoft paper, Sparks of AGI, and so it seems that the most relevant, the most updated version of the LLMs, and again, Claude 3.5 and GPT-4o can reason pretty well. So how does my intuitive feeling when toying with ChatGPT is lacking, your theory of this is not intelligence.
Okay, so great question. So you're making the claim that GPT-4 does pretty well, and I would say it depends
on reasoning tests.
On reasoning tests. Okay, on
yes.
reasoning tests. Okay, that's fine. I would invite you to think about a human being that does relatively well on reasoning tests, but every once in a while goes crazy and does something terribly violent or completely unexpected, but not very often. Just every once in a while, something goes terribly, terribly wrong.
You just described my teenage kid.
Yeah, well, yes. Teenagers are a great example of a particular kind of embodiment. Absolutely. And you can never guess when it's coming. You never know when it's coming. So if you're happy to rely on human beings that do well on an IQ test most of the time, but every once in a while they put their pen down and they go completely bananas, if you want to count that as doing pretty well, okay. But that's the framing that a lot of these large AI corporations are trying to impose on all of this. They want us to subscribe to the view that that's okay. It's okay if most of the time these machines are okay, but every once in a while they go completely off the rails. And the community says that's not okay. That's not okay. You need, if there are machines that are going to exist with us here in the real world, they have to be reliable 100% of the time. And that is a much higher bar, a much more difficult goal to achieve. But that's it. We can't rely
on...
Yeah.
You challenge the common wisdom that, maybe people, at this point of the conversation says, okay, I can understand why in physical problems that I propose to the AI, I need the concept of embodiment because I need, to act in the real world. But it is very strange that the constraint of embodiment can be, can be injected into pure reason problems. How is it so? Because we tend to think that we have the logic up here, and the logic up here has nothing to do with the rest of the body, that this is a very non-intuitive idea to grasp.
Absolutely. It is very tricky. And another way to think about this is a lot of our reasoning abilities and our abstractions, mathematics, poetry, painting, these things that we think of as, in English, we would say cerebral, literally coming from the prefrontal cortex. These things are rooted in the body. So even in a reasoning task, Every once in a while, most of the time, GPT-4 does perfectly well. But every once in a while, GPT-4 answers a reasoning question with something that is not just wrong, but crazy wrong. Like it demonstrates GPT doesn't really understand. And that sounds like kind of nitpicking. But again, that's a hallmark of intelligence is even on a reasoning task, even on an abstract tasks, when you're wrong, you should only be wrong slightly. You're asked a mathematical question, you should respond with a number, even if the number's wrong. But if you start drawing or doing something else, you're failing in a fundamental way. And that's what tends to happen with GPT-4 and these other non-embodied AI systems. When they fail catastrophically. They don't stay within the structure of the abstract problem. And the reason why is they don't have an inheritance of having a body, being constrained by the world.
So
I'll give your audience a concrete example. I
Oh.
forget which AI system it was, but there was one that was recommending you put glue on your pizza.
Yes,
Remember this one?
yes. I remember. I think it was ChatGPT.
Okay, it's an abstract task, reasoning about how to, make something. It's still
Yes.
all language and talking. That system, if it was ChatGPT, was confident, but didn't realize that glue is not an ingredient. It doesn't fit with all the other common ingredients. So it wasn't just getting it wrong by putting pineapple on the pizza, which Italians would disagree
Okay.
with. It was really wrong. It recommended something that goes beyond pizza into something that is physically dangerous for a human being. That's the hallmark of flawed, non-embodied systems.
And again, what you're saying is, it is absolutely true that in ChatGPT 3, the percentage of such error was, let's say, 20%, and in 3.5, it was 10%, and in 4.40, it's going to be just 0.5%. Very good. Most of the time, it nails the problem. But the 0.5%, like, give an evidence that in the other 99.5, the true genuine understanding was lacking there. This is basically what we're saying.
Well, maybe the problem there is that people disagree on what understanding means. So when I discuss about embodiment, I like to focus on that 0.5% of the time when things go wrong. Everybody agrees that putting glue on pizza is not just wrong, but very wrong. So the nature of the mistakes that a non-AI system makes is everything. That's what we should be measuring. Not how often it makes mistakes, it's what happens when it goes wrong. A human being will not put glue on a pizza ever, 0%, because embodied humans understand fundamentally that is, you just never do that. So it's not how, the percentage of which the percent error of ChatGPT version XYZ, that's less important than when it makes a mistake. And it makes mistakes, humans make mistakes. What happens during those mistakes? Embodiment helps ensure that those mistakes are less dangerous, less fundamental. That's the inheritance of having a body.
Okay, so let me give you an example, and please tell me what you think about this example, because Gary Marcus gives a lengthy description of what he means by common sense, okay? And the idea is, why would people say that this image is funny? In order to understand why this image is funny, okay, we need to understand many, many things. For example, we need to understand that this is a president of the United States, and if the president of the United States is doing like a hoax, it's going to be funnier. Again, we need to understand that the idea of weight measuring can be influenced by the leg, and we also need to understand another thing, that, and very important thing, that in our modern time, to wait more is bad. Without understanding all of those things, the joke doesn't make sense. So would you say that the concept of this image is embodiment or common sense and embodiment are
Yeah,
tangled
great question.
together?
Yeah. So you can imagine a non-AI, a non-embodied AI system like ChatGPT actually getting the joke. If you provide enough images of things like that, you can imagine an infinite set of variations on that, then yes, you could train a non-AI system, a non-embodied AI system to quote unquote get the joke. Now imagine an embodied system which is looking at that image and it's feeling or simulating how excited it would feel if it saw that it lost 5 pounds itself, that the embodied system can feel the happiness that that person on the weight is feeling. And then the embodied AI system can feel the dejection, the drop in the stomach when you turn around and see that somebody had their foot on the scale and you feel
Or the
depressed.
president of the United States,
And
which
then you
is
look, and the third step, you look and see it's the president who stepped on it, and now you feel the laughter and you're simulating inside all those actions and feelings. So both, I would say, Gary Marcus tends to put that up and say, oh, a non-embodied AI system would never get the joke. I differ with Gary. I would say, yeah, a non-embodied AI system could get it if you gave it enough training examples. But it's not arriving at the joke in the same way that an embodied AI system is, and that makes all the difference.
And what you said right now about the idea of like let's think that embodied AI system will feel brings me to the idea of mirror neurons. Okay, the idea of that some of the neurons in our brain can react when we see people do a certain task, the work of Risoletti. But we don't have such systems in deep learning. The idea of artificial or deep neural networks is profoundly different from what I understand than what you propose. So let's deep dive to the concept of what an embodiment AI system will look like. I have Python, I have TensorFlow, I have PyTorch. What do I do?
Yeah, okay, all right. I want you to imagine, what should we call it? Embo Torch, embodied torch. It is a programming language that is connected to a 3D printer. You can write code and you can also print machines that push against the world and feel the world pushing back. That's the basis. Inside of that system, instead of coding up neurons that transform matrices and connection weights and backpropagate error and compute loss, you're programming a whole bunch of things that push against the world and push back. And some of those things that you're programming are going to be sent to the 3D printer and printed out. And these are going to be little, small, simple machines that are combined into bigger and bigger machines. My colleague Mike Levin says that humans and every organism on the planet is a machine made of machines made of machines. We are an organism made of organs, made of tissues, made of cells, made of subcellular components. And each living component in us, we are living hierarchies. Each component of us can push against its environment and feel how the world pushes back. The cell has thousands, if not millions, of sensor and motor components on the cell surface. That's the embodied equivalent of PyTorch, making machines that push against their world and feel how the world pushes back. But we are making or programming or figuring out how to create hierarchies of embodied machines in the same way that PyTorch makes hierarchies of neurons and layers and up you go. Same idea, but in an embodied framework.
Wow. Okay. Basically, what you're saying right now, and again, I went over some of your joint work with Mike Levin, which I consider some of his work to be mystical, when a cell, I think when in our conversation, he said something like, when a cell is dead, maybe it has like this I don't know how he put it, like a notion of a bigger thing above the cell that it submits to. But the idea of Mike Levine and your joint work with Xenobots basically said, listen, building robots with metal and aluminum and even with electricity, like in electronic engineerings, can be profoundly different than building biological robots, a xenorobot, okay? And maybe the idea of the concept that we can take a cell, a nerve cell, a neuron, and say, okay, we can simulate it into a perceptron, a very simple sigma WIXI. This is where the mistake was, because you can make like it's like the essence of sim to real. This is not a nerve cell. This is something completely different, and you can go to the level of intelligence just as your simulation will be real. And perceptrons are not even close to a simple nerve cell.
Agreed. Agreed. Absolutely.
Okay, so what do? With all the electrical engineering, we all we all the import Python. So basically, we come to the plateau of artificial intelligence as we now know it. I think this is the idea of Jan LeCun. Ken Stanley from OpenAI told me the exact same thing. The GPT-5 will be much less impressive, or the leap between GPT-4o and GPT-5 will be much less impressive than the leap between GPT 3.5 and GPT-4. We need
Correct.
a different approach.
Absolutely.
Okay.
Absolutely.
Okay. So, which leads me, to the little mystical thing. Basically, the idea of artificial general intelligence cannot be duplicated without the concept of biology. We need biology.
We need embodiment. We need biology. Absolutely. What AGI means a lot of different things to different people, but yes, we cannot get there without those pieces. Agreed.
And again, so which leads, which sheds some new light on the Turing test and the Chinese room test, etc., etc., etc. The idea of, John Searle idea is that we can't, this is not an understanding, the idea of the Chinese room. Hence, we need a different model. The model of manipulating data, the model of universal Turing machine, can be reduced to the paradox of the Chinese room. Hence, those models cannot create pure understanding. Therefore, we need a different mechanism, and the different mechanism can be or must be biology, where, like, I will say that you have the fingerprint of God, something, the idea of something that beyond what you can create, but you can say that it has the fingerprint of nature.
Yes, absolutely. So what is it in biological systems that's missing from the Chinese room and all of our digital electronics and Turing machines? Now, people disagree about what it is in biology that's missing. My view is it's the embodiment part. It's the fact that every single biological component, from the subcellular to an entire ecosystem, all of those things push against their environment and observe how the environment pushes back. That's the fundamental missing piece. You talked about neurons and Turing machines and the Chinese room. They all have a very different fundamental atomic building block, which is wait for data, process it, and then output data. It's the opposite of what biology does.
And again, the concept of self-healing, the concept of the tendency, I think that we need to move on to the Xenobot. But in a recent podcast that I hear you explaining about all the things, you said, I have a biological robot, which we call the Xenobot, and you can think of it like a circle, and you can cut it like a Pac-Man, okay? So you have a hole in the circle, and this robot, like I don't know how many frog cells there are in this robot, but this robot can fix itself without ever being told to. And this robot can, combine and emerge and stick to other robots without being specifically told to do it in the software.
Exactly. Exactly. So this, to me, as one of the co-inventors, is one of the things that's so amazing about xenobots is they seem to do what's called in machine learning zero-shot learning. When they're presented with a surprising event, like being punctured or an injury or placed in a new environment, they know immediately what to do. And how is it that biological systems know how to do this zero-shot learning? It often looks like a magical thing or a spiritual thing, or, like you said, the thumbprint of God. As a roboticist, what I see is that thing must have had a broad range of sensor motor experiences. It's been pre-trained, again, to use a term from machine learning, to deal with surprise. When non-embodied AI systems exhibit zero-shot learning, when they correctly do the right thing with no additional learning, it's because they've been pre-trained on a large set of experiences. Same thing with embodied systems. So what is that pre-training?
Evolution.
Evolution is part of it. Absolutely. That's part of it. I call it morphological pre-training. So if you look at the cellular level, forget evolution for a moment, you're right, that's a part of it. But even during development, we all start as a single cell. And in the case of humans, we grow into 10 to the 12 cells. We cross 12 orders of magnitude, and we keep ourselves alive during those transformations. Can you imagine the breadth of experiences that an individual cell has as we develop? It's constantly changing its neighbors. We talked about neurons. Neurons tunnel through other cells. They grow branches. They connect to things. Those things feel poisonous, and they pull off their synaptic trees, and they grow in other directions. Neurons themselves are moving, growing, changing partners, pushing against their environment, feeling how the world pushes back. You're a constant flux of cells. So when we as a human are presented with a novel environment, like a chessboard in a configuration we haven't seen before, that kind of surprise is trivial compared to the surprise that all our cells feel all the time. That's the pre-training. And then you mentioned evolution. We're just talking about the development of a single human being. If you keep going back to the ova and sperm that produced that human and trace that ovum and sperm back into your mother and father and their developmental trajectories, you can keep going back 3.5 billion years. And it is a continuous dynamical system that has not stopped in all that time. Our cells and our bodies, back to embodiment, have been pre-trained on so much surprise. Those cells push on the world and get a surprising result back that computers and airplanes and space stations and chess and all the rest of it, I mean, it's new, but it's not as new as these other experiences. That's morphological pre-training.
Wow, this is so true. The idea of a new, unfamiliar situation in chess or in a flight simulator is so tiny compared to the idea of the work conducted by your colleague Mike Levine, when he takes eye cells from the brain and puts them on the tail of the frog,
right?
and the body. And I think this is the essence of embodiment, because the eye cells can trace, and everything can be connected. Let's say that I take a LiDAR, an I2C LiDAR, and I just connect it to the vehicle, and somehow all the connections, all the codes can magically connect, and all the I2C SPI UART code, everything can be connected together. This is just science fiction. And the idea is but this science fiction happens every day. It happens every day in our body.
And I would say that's the part of biology that's missing from all of our AI, from the Chinese room to ChatGPT to Turing machines, all of those, and traditional robotics, autonomous vehicles. Every single one of those technologies, either physical or hypothetical, are missing that piece. And that's the piece that's important. That's embodiment. If we want machines that are smart and safe, they need to know how to keep themselves alive and safe throughout massive reconfigurations over time. If you then equip them with their equivalent of mirror neurons, like you were mentioning before, they can now reason about how to keep others safe. Right? If you can keep yourself safe through the churn and flux of development and everything else going on, you are in a very good position to be able to recognize and know how to keep others safe. And to me, that's the path towards artificial general intelligence.
And it seems like that you have everything, you know, on your libraries. Let's say that you have import biology, yes, on your Python torch, you have everything. You have mirror neurons, and you have this zero-shot learning. I think, you know, the idea of zero-shot learning is so important, because on my lectures, I think, in my lectures, I I speak about the difference between a baby and then machine learning that can distinguish cats from dogs. Okay, a baby can do it after seeing two examples of what is a cat, what is a dog. But a machine, a Google AI, VGG 16, needs millions of pictures. This is not zero-shot learning. The idea of, and I think that this is crucial, that many people say that machine learning are great at predicting the past because you learned from a certain distribution. Hence, you can only manipulate or act or be relevant to this distribution. This is why machine learnings, from as far as I'm concerned, cannot predict the price of the Bitcoin in the next 20 months, because the price of the Bitcoin will come from a different, unknown, unfamiliar distribution. So before we move on to the xenorobots,
sure.
Since you're a roboticist, what can we do right now? So what will be the horizon of AI robotics without the use of biology? Let's say how, or put it differently, what other progress or could we expect from Boston Dynamics or other great robotic companies to conquer?
Yeah, great question. So we have to stop making robots out of metal and plastics and ceramics, because metal and plastic and ceramics are dead, inert material. They cannot on their own push against the world and observe how the world pushes back. We are in trouble. If the central processing unit of a Tesla autonomous car gets knocked out, the wheels and the rubber that makes up the wheels, they cannot adapt and try and, halt the car. But again, biology has actors, embodied actors at every scale. We need to start building machines out of machines, out of machines, out of machines. And we could do that today. We can make very small machines that push and observe. We can compose those machines into larger composites, and just starting to make machines, again, out of non-biological materials, but building up hierarchies of machines, that's the way forward. You can imagine an autonomous car built in that way, where if the car is cut in half, or one of the wheels falls off, or there's an electromagnetic pulse that knocks out the electronics of the car, parts of the car can react. They can take over, and they can mitigate the disaster. They can make it less dangerous to the occupant and anyone on the road. That's what biology does, and we can start to build that today into non-biological components if Boston Dynamics and these other companies start to think in an embodied manner.
But can you think, but okay, so since you are an embodied agent, let me push you, okay? Let me push you. And
please do.
Okay, let me phrase it more bluntly. Would you say that in the RoboCop a soccer competition in 20 years, robots made out of metal and plastic can win human beings. Okay?
Yeah, yes, but that's uninteresting. What I'd like to see is a robot team win the RoboCup and then be placed in an arena that's 10 times the size, so that the players have to climb on each other's back and solve the problem at 10 times the scale, or 1/10 the scale, or solve a different sporting event. Again, the RoboCup and all the rest of these competitions, they're an inheritance of this 20th century way of thinking of, the brain and technology and the Chinese room. It's the wrong way to think about things. You can have a robot that wins RoboCup or wins the World Cup against humans, but that doesn't mean very much. That doesn't mean you've achieved AGI or that you're anywhere closer. We are adaptable creatures, and that's where intelligence and safe action comes from.
So from what I understand, my hunch, my intuition is that one cannot build fully embodied AI robots without the use of biology. We can't just take the idea, the notion of biology that you advocate so much, because we did it with the artificial neural network. We had, okay, let's take the perceptron. The idea of sim to real, the idea of, okay, let's simulate the idea of biology is bound to fail. If we don't incorporate biology into our robots, my intuition is, according to what I read from you and what I know, is bound to fail. We can't just take biology as an inspiration. We must take biology into the mechanics and the engineering of our robots.
You might be right. I guess I don't know. I don't know what the answer is. Can we, if we actually inspect biology in the right way, can we actually be smart enough to know what we need to distill out of biology into non-biological machines? Maybe we're smart enough to do that. Maybe not, and we need to literally incorporate biology into machines in the way we did with xenobots. I don't know. The safest thing is probably to try everything and see what works.
And again, the idea of, because, if what you're saying right now is true, maybe the idea of perceptron as sigma wi xi is insufficient, and we can come with a much broader, much more complex idea of neural network and, start from scratch and, develop a new backpropagation idea that somehow maybe, just maybe, in the context of reasoning or large foundation models, can bring great results. Maybe the idea of perceptron is the first thing that we need to change according to what we know right now from biology.
That I agree with. The perceptron is maybe necessary, but not sufficient. There are other things going on in biology that we have thrown out when we created the deep learning revolution, and those need to be in our machines, regardless of whether those are inorganic or organic machines.
Okay, so we said so many times the word xenobots, and we must explain. Xenobots are the idea of a joint research with you and Dr. Mike Levine, two great researchers, if I may say, and of course I may because it's my podcast. And the idea is that you wanted to collaborate, and this is the beginning of every good research. Okay, two people say, we want to work together, we just don't know the subject yet. And the subject arrived, and the idea is, can we use some of the things that Mike does and some of the things that you do together? And the process, or the answer, was Xenobots. The idea of taking a Lego brick cells coming for frogs and manipulate them in a way that those robots can move forward on a petri dish. And you use a genetic algorithm approach, evolutionary artificial intelligence approach, in order, to simulate the correct or the correct configuration for the robots to move forward, and you have like this giant microsurgeon genius that can actually cut and paste on the cell level. So how close did I get to the idea of Xenobots?
You got it exactly right. The AI dreams up a way to reconfigure frog cells to produce something in simulation in a video game that looks and acts nothing like wild type frog. So it is something the AI predicts will survive and do what we want it to do. And in my book, that's why it counts as a robot. It's a machine that's been designed to move around and do something that humans want it to do. No genetic manipulation whatsoever. This is not GMO. This is something completely different. And then Doug Blackiston, the microsurgeon that you mentioned, he takes what the AI dreamed up, looks down through the microscope, and microsurgically takes genetically unmodified frog cells and tries to build it. So if you were to ask Doug, he would happily say he's the AI's human slave. He just builds what the AI tells him to build. And what comes out the end of that pipeline is a strange thing, the Xenobot. It's something that's about 1 millimeter across. So if you were to watch this thing in a petri dish in water, it would look like a moving speck of pepper. You can just barely see it with the naked eye. And the Xenobot, we're still wrestling with what exactly it is. It kind of is a frog because it's made from frog cells, but also it's not a frog. Is it a robot? It's kind of a robot. It's kind of not a robot, or at least not a robot we're familiar with. It's a new kind of thing.
Can it vote? Can it vote in the next election? Can it vote?
Does it have a soul? Is it conscious? Can it think? Can it feel? Can it experience?
Can it swim? We know that it can swim. We know it can swim because what you took are skin cells, and in the skin cells we have tiny bits of hair. So during the process of genetic algorithm, it learned how to move the tiny hairs in order to swim in water.
That's right. Exactly.
Just a second. This is not science fiction. We are not talking about Lord of the Rings or Asimov. We are talking about peer review published journals, because some of the things that we are talking about now, it can't be real. Okay. So I want to make sure that everyone understands that you took cells and glued them together in a very mysterious way. And those cells can do what they are told to do. Now, again, you can't, you don't have a remote control, go left, go right, okay?
That's right. That's right.
But according to the genetic algorithms, after several thousands of years of, which is approximately 1 week at a mega, 1 week at a mega supercomputer, it can move forward, okay? Or I can, program it to move forward and then move left, okay, etc. If you're familiar with the idea of genetic algorithms, this is relatively simple. On your podcast, you said that the process of the fine-tuning was relatively simple, but the process of the simulation was relatively complex. Could you please elaborate on the concept of the simulation?
Sure. So the simulation it looks like a video game. It's a virtual 3-dimensional world in which we code up some physics, what's going on inside the water of a petri dish.
It's like Unity? It's like Unity?
It's like Unity. It's not Unity, but it's an equivalent. That's right. So there's basically we build a physics engine that all incorporates physics like gravity and Reynolds number of the water, a little bit of fluid dynamics, and then it's also a biophysical model. We're building in, you mentioned the cilia, these small hairs. So we have to tell the physics engine how to simulate these small hairs. That code is thousands and thousands of lines long, but once that's done, we wrap that piece of code in what you said, a genetic algorithm that is a trial and error process. It tries putting a frog skin cell next to a heart muscle cell. That evolutionary algorithm is 13 lines of code long. It's unbelievably simple. That part is simple. And the part that Well, I guess there's several parts that sound science fiction to folks, but the fact that this simple trial and error process could find a new way to reconfigure frog cells that works, that produces something that's viable
Mhm.
and is not a frog, the fact that it was so easy comes back to what we were talking about embodiment. From the point of view of those frog cells, they are masters of zero-shot learning. The frog cells, in effect, are saying, oh, you want us to now cooperate in this new configuration? No problem. We'll grow our cilia and we'll beat the cilia against the water and we'll move. Again, we're leveraging this fundamental feature of biology, embodiment, being able to adapt to changes in the environment.
Let me ask you something that I thought about when hearing the podcast. Basically, the idea, the basic or the most important problem when dealing with such a simulation is moving to the real world, what we call sim to real problem. You have the simulation, and in the simulation, you have, okay, you need to take this cell and combine them together in such a way, and your great microsurgeon, Doug,
Yes.
kudos for Doug, uh, can do it. And then this idea, would the new frog or the new, I don't know, Xenobot move forward? Okay. This is the basic idea of sim to real. The other, the other idea of sim to real is, let's say that we have the embodiment and we have the zero shot learning. Maybe since we are dealing with biology, okay, the simulation cannot simulate new environments. So maybe the Xenobot as performed on the simulation will fail when dealing with new unfamiliar situation, but the exact Xenobot as was built by Doug, since it is a biological mechanism with all the embodiments, can move this obstacle, can
That's
overcome this obstacle. So
that's
this is
exactly the
the
point,
all
Roy.
the this is exactly sim to real on background.
Yes. You that's exactly it, right? All living tissues are masters of dealing with things that are not quite the way they used to be. Living tissues have 3.5 billion years of experience doing that. So again, the rearrangement of frog into xenobot from the point of view of the cells, it's not such a big deal. They can do it. And again, as a roboticist, having a front row seat for all of this xenobot research over the last 6 years, my mind is still blown because this is not how robotics works. Most inorganic machines, they do less than what we hope they would do. Any change in the environment, they break down. They're unreliable. This is the opposite.
And again, again and again and again, this is so mind blowing. The idea is that you cannot simulate this zero shot learning on the simulator, because if you could, you could implant this code into the Tesla. The idea is that
Exactly.
we cannot simulate it. Only we get this feature only when we say on Python import biology. This is the idea.
Agreed.
You
Agreed.
know, I
Absolutely.
worked in a robotics lab for, I don't know, like 6 years. And all of us, occasionally you can see a spider, in the lab. And
Yeah.
I always thought of a spider in a robotic labs as God making fun of us.
Yeah.
The idea
Good.
of,
Great point. Yeah.
wow, listen, and
Yeah.
it can
Yeah.
procreate. It can
Yeah. Exactly.
procreate. I
Exactly.
can't,
Exactly.
I will give you 2 Raspberry Pi. In a million years, you don't come with the 3 little Raspberry Zero Pi.
That's it.
And
That's
again,
it. Exactly.
what you're doing right now in your front seat row is basically trying to manipulate the spider, manipulate the biology.
That's it, exactly. Rather than trying to simulate the spider, why don't we just incorporate parts of the spider or parts of any organism into what we're trying to
Mm.
do? We being the entire AI and robotics community. That's
Okay, well, so where is the research right now? I heard, I think, like 1 year ago. About the podcast was recording one year ago, and I know you, I know Mike. You are both extremely, uh, extremely smart and extremely not lazy. I don't know. I not
We
la-
are not, we
so
are not lazy. We're not sitting still. Yes,
yeah,
that's right.
you are not sitting still. So where is this research right now?
It's going in many directions, and some of the directions I can't talk about yet, but stay tuned. We recently published a paper not about xenobots, but about anthrobots, bots that are made from human cells. So you can imagine the anthrobot starts to open up all the possible medical applications of this kind of technology.
And the body will not reject them because this is part of the human body.
That's it. So there is a whole research program now where we're trying to
Mhm.
expand the palette of cell types and organisms that we draw the cells from and make that larger palette available to the AI. Maybe AI can figure out how to cobble together different cell types from different organisms to produce a biobot that does whatever it is we want it to do. These are the chimera bots from Greek mythology, the chimera that's made from different animals. Chimera bots are a possibility. We're also looking at scaling up this technology. So we talked about Doug, this microsurgeon. He's extremely talented. It takes him 4 hours to make 1 millimeter sized xenobot. Xenobot meat is currently the most expensive meat on the planet, as you can imagine. So, can we remove Doug from the process? Can we get rid of the human slaves and automatically manufacture large numbers of AI designed biobots?
How does the work of Neuralink right now is we know what they're doing. I don't know how many people are precisely know what they're doing, but the idea of, okay, can we take all the electronics that we know right now, all the silicon, and incorporate way into biology? I think that this is the idea of Neuralink as a like just connect an SD card to your brain and learn jujitsu like Keanu Reeves on the Matrix. So
Yep.
how does the work of combining biology with electronics
Yeah.
can affect or differ from your work? Or you're also, planning on maybe incorporate some electronics into the next version of Xenobots.
Yeah, maybe. I think it's a good point. So in both cases, so in Neuralink, you have some traditional digital electronics, which is influencing the cells, presumably in the central nervous system or peripheral nervous system. In our case, you have a human that's mechanically pushing frog cells around using very small instruments. But in both examples, you have technology or humans that are trying to influence biology to do something it doesn't usually do, or at least get it to do it faster in the case of learning jujitsu in the brain. So I think they're not mutually exclusive. They're just our attempts to figure out how to convince biology to do something slightly different from what it already does. And the $1 million question, and probably the $1 billion question, is what's the right way to persuade biology to do what we want it to do? Is it a combination of microsurgically rearranging tissue? We flash images and video onto cells that are photosensitive to convince them to do different things? Do we send electrical impulses from an SD card?
Bioelectricity, like Mike Levine love to
All of
say. Okay,
that. Yeah.
the
So I think it all
the
fits together.
the idea is how do you conceive the concept of a remote control to the Xenobot? I think this is basically what
Oh,
we're talking right now.
I
How
see.
do we even conceive the idea of how
Yeah,
can I, how can I, change your
yeah,
target function
yes.
while
Okay.
you are on a different target function? Move left, move right,
Yeah,
move
yeah,
backwards.
yeah. So there, one possibility would be to add neurons to the xenobots, give them brains, and then try and program the biological neurons inside xenobots. That's one possibility. Another possibility is to apply external fields. So you apply an electrical current to the cells that cause the xenobot to turn left and right. And that would basically be the equivalent of the remote control you mentioned. Better still would be for an AI to figure out how to put the cells together so that they now interpret microplastics as food. So we humans are, and every organism is driven by reward and punishment. We feel a rewarding signal when we eat something tasty. You might be able to convince the cells to view microplastics as food. And if you can, now you have a little tiny Roomba that instead of cleaning up dirt, it cleans up little bits of microplastic from the water. You convince the biobot that eating plastic is in its own interest. That would be the ultimate way to quote unquote program biobots.
Wow, it's like in Tom Sawyer when he convinced his friend to paint the
That's
fence.
it. Exactly that. I love that. I hadn't thought of that. That's it. You want a Tom Sawyer AI. How do you convince the cells to want to do that?
Oh, so also I feel good that I gave something in return to this great conversation. Wow. Okay, Josh, thank you so much for your time, your research, your explanations, and what you do for humanity. I really hope when the Xenobots will take over humanity, they will come to you last. Okay.
Thank you for that. I hope so too.
Okay, now I think I have two more questions, which are final questions. Since most of us, when we think robotics, we think of Arduino, Raspberry Pi, and the other things. What will be your advice to a person, even an electrical engineering student, or mechanical engineering student, or computer science, or just a young 16 years old boy or girl who wants to go deep into the worlds of robotics? What will be like your great source that you can recommend, or great online course, or a great book, or a great YouTube playlist, or something that you say, this is very good for a beginner?
Okay. I would recommend Richard Dawkins' books, The Selfish Gene, some of his other books. I would recommend the philosopher, Daniel Dennett.
The late philosopher.
The late philosopher, Daniel Dennett, may he rest in peace. One of Dan's greatest books, in my opinion, is Darwin's Dangerous Idea. There are many philosophers and biologists out there who they don't write books about biology saying protein XYZ does this, and they abstract away from biology what is so special about biology. And that's kind of what we've been talking about this past hour. So I would invite young people to try and find books that are about biology or biology adjacent that get at the fundamentals of what is so special about biology.
Okay, thank you. And a last question, as a young professor at the university, since you publish so much and you do so many things, my question is, what will be your advice to be productive, to productivity? Okay. I had many people on the show, each one with a different productivity tip, and I would like to listen to your productivity tip.
Okay. Yeah, I would say no matter whether you're a young person or not so young person trying to get into this field or contribute to AI and robotics, is follow what you're curious about and what you're excited about. That's the most important thing. There is so much advice out there that you have to learn PyTorch, you have to learn forward kinematics for robotics. There's advice about what you should be focused on. I would say ignore that. Read Dan Dennett, read Michael Levin, read Richard Dawkins, read these people that inspire you. And then when they talk about things you don't understand, go research those things, try and code them up, buy a Raspberry Pi, try it out. When I was younger, the thing that got me out of bed at 5 a.m. to be productive was not me waking up saying I have to be productive. It was me saying I was working on this till late at night. I got to get up and finish it. I want to know what happens.
Wow.
Follow your excitement, follow your curiosity, and you will be productive. And if you're productive for long enough, you will contribute to our intellectual community. You will discover new things that humans have never known about before.
And I think that in our next conversation that must happen, we will talk about the idea of creativity. Okay?
That would be great.
Josh Bongard, Thank you so much for your time. Thank you.
My pleasure, Roy. This was wonderful. Thanks.